welcome everyone. I guess we can almost start. Waiting for a few people to enter the room. We can already start maybe with the introduction. What I will present today is maybe a typical talk for Drupal community, since I will not be talking about Drupal. I will be talking about the NPM JavaScript ecosystem. But still, I hope that the lessons or the things I have to say about it and the lessons learned about it might be beneficial for you as developers of websites or as people that might use JavaScript or JavaScript packages throughout the development. So maybe let me talk a little bit about myself first. So that's another atypical thing. I'm not really a developer, I'm more a researcher. So I'm a professor in software engineering at the University of Mons in Belgium. I live in Ghent, so it was not really difficult for me to come here, just 10 minutes of bicycle. The main research topic of our group, this is 3 members of our group, 2 postdocs and myself, and there's all the PhD students, which are these red circles here. We are basically doing research in analyzing large open source software ecosystems. So examples are NPM packages, Ruby gems, CRAN, CPAN, large open source ecosystems, including the packages developed by these ecosystems, but also the communities. So our main goal in a couple of research projects in which we are involved is analyzing the health of these software ecosystems. And that's what I will be talking about today. So to do this, we are basically doing what is called software repository mining. We try to extract large data from the the history that is available in these open source communities. We can extract this from the source code repositories, from the mailing lists, from the bug data, every type of data that is stored in open source. We can rely on this to analyze what's going on. And of course, once we have done this, we can validate this with the real persons involved in these communities. In this talk today, I will be mainly focusing on some very recent research we have been doing on the NPM packaging ecosystem. Here today I talk specifically for NPM because I think that's the most relevant for this community. Since of course NPM JavaScript is used extremely frequently today for developing websites or within the development of websites. Whenever you want to build some website, it's very likely that there will be some JavaScript involved, either directly or indirectly, or that you will use directly or indirectly some NPM package, maybe even without even being aware of it. So maybe a little bit more about the general context of our research. We are also involved in, as I mentioned, in a couple of research projects. There is, for example, I don't know if you have heard about this, the Chaos community. That's the Linux. It's one of the big Linux Foundation projects. Chaos stands for Community Health Analytics for Open Source Software. So it's basically a consortium of researchers, also companies that are basically concerned about community health in open source software. And basically, they want to try to improve the health of their open source communities. And health can mean many different things. It can be the social health, it can be technical health, whatever type of health you can think of, it will probably be in. So basically, whenever you have a big open source community, like Drupal or any other, we want to try to focus on the health of these ecosystems. To do this, we need ways of measuring health, ways of analyzing health, ways of providing tools that can help you to improve the health, and so on. So if you want to know more about this community, there's this website chaos.community where you can find more information and all the different partners that are involved. So it's supported by the Linux Foundation that I already mentioned. Within this big, huge project, we are involved as university in some smaller collaborations. So we have one project about software ecosystem health together with 2 universities in Quebec. Polytechnique Montréal and University of Laval. And within Belgium, we have also another project about Seco Assist, which is basically the same, but this is a joint partnership between University of Mons and Namur in the French part of Belgium, and then we have Antwerpen and Brussels, VUB, in the Dutch part of Belgium. So all of this focusing on these aspects of open source software ecosystem health. So I said, what does software health mean? Basically, there is not really a fixed definition. There is lots of different interpretations. You can ask, what does software health mean to 25 different persons? They will all give a different definition. Basically, here you can see some terms that are typically attributed to a good health of your software system. If you have a software system or a collection of software systems, it will be healthy if it will be successful, it will be surviving over time, it will be resilient to changes, it will be sustainable, it's growing over time, it has a sufficient diversity in people working in the project or in features offered by the product, it will be popular, and so on. Okay, so these are, let's say, the good things. This is about a healthy software ecosystem. Now, what are the problems? Why are software ecosystems unhealthy? So here, this depends on the particular dimension you're focusing on. You could have problems with the health because of social problems within your community, because of technical problems, because of legal problems. Think about software licensing, business, organizational problems. So here I just focus on two of these dimensions, the technical and the social ones. Technical problems are typically due to the well-known dependency hell. You have some package, some software that is depending on something else, that is depending on something else, and very quickly you have a bunch of dependencies and you don't know how to deal with it. Other problems are problems with software that you depend on that is outdated, or basically it's not maintained anymore. What do you do? Security vulnerabilities and bugs, well known and clearly health related. Quality problems in your code, technical debt. All of these are technical problems within the source code that you're using or developing yourself. Social health is more related to the persons developing these systems. So, for example, you might have a healthy system, but the key developer in your team is going away. What you're going to do? Can you replace him? If this person has the key knowledge in your team, if he goes away, it's maybe very difficult to find a replacement. So this is the well-known bus factor phenomenon or truck factor phenomenon. I don't know if you have heard about this. It means what happens if your key developer gets run over by a bus. Then you have a problem. Other problems are having to do with how different teams within your organization are communicating or interacting. There might be bad communication practices. There might be not sufficient social diversity or not sufficient cultural diversity or simply cultural differences, which might lead to misunderstandings or social conflicts. So that's lots of examples about social health. So in our research, we are focusing on both of these factors. Today, I will be mostly talking about the technical health factors, but we also have some results on social health. But that will be another presentation. So let me now start by motivating some examples for these technical factors. I guess you have, who has heard about the left pad problem? Okay, a couple. So for those, not as much as I would expect. So this is a typical example of a problem in NPM that had a major impact not only on NPM but on lots of websites being developed using something where the people that were developing this website didn't even know about this package. I also didn't know about it. Fortunately, I was not developing a website. So basically, this is basically a very small, tiny package within JavaScript that was developed by some guy, and at some point in time, for some social reason, I can explain you offline what was the exact reason, the developer of this package decided to remove his package from the package manager. What happened at that moment? Basically, this package had a couple of thousands other NPM packages that depended on this package. And suddenly, these packages could not be, whenever you wanted to install it, it had a direct dependence on this left pad package, and you couldn't install the package. lots of packages, including Node.js, was depending indirectly on LeftPad, and because of this, websites using Node.js couldn't be run anymore, couldn't be upgraded anymore because there was a package missing. Basically, it was actually this LeftPad package was completely removed, and it was not available anymore, so installation problems for lots of websites. It had a lot of attention from even journalists who, maybe a little bit extreme, said it almost broke the entire internet. But it was exaggerated, but it was still a very big problem at that time. So basically you can see it's like removing one block and everything falls down because everything depends on everything else. So this is related to dependencies and to software that is becoming obsolete or unmaintained. It was not really obsolete, it was really useful, but someone removed it. So it's the fragility of your ecosystem. The fragility, you can see this here, I don't know, it's not very clear with the lighting, but this is a picture showing the state of the NPM dependency network in April 2016. There's lots of lines here. Basically, you find a huge cluster of spaghetti of all your NPM packages depending on each other. We try to count how many packages depend on each other. Basically, 60% of all NPM packages have at least one dependency to any other, so you have a huge connected dependency graph where if you take one of them, you find 10,000 other packages linked to it. So here I'm just going to show you a particular example. Okay, I took an example, one of the examples in NPM where I found Drupal, but actually I don't know what it's doing. It's not really a real package. It's version 0.0.0. I think it's maybe someone knows about this package. I tried to look in it, but it's very new, it's not really doing anything. Maybe just to have an indication about which are the NPM packages that Drupal 8 depends upon, because it really doesn't contain any code. But it's just to show you the example. So this package depends on about 5 other packages. So that's quite manageable, you can still manage this, but indirectly, this package depends on MySQL. MySQL itself depends on 5 other packages. Still manageable, but this depends on this one, which again depends on about 10 other packages. This is feasible, that's about 20 packages, but the main problem is whenever you're the developer of the first package, you only have a small view on the problem, you only will look at your direct dependencies. Most of the existing dependency management tools will only know about direct dependencies. I don't know of any major dependency management tools that look into the transitive dependencies, simply because it's so costly to compute, especially if you have a very dense transitive dependency graph. So that's a problem that has to do with transitive dependencies, which is directly related to the LeftPad incident I have mentioned before. Okay, another problem that, someone this morning talked about is also about the increasing complexity. So basically, okay, I take here another example, a very simple HTTP client request package. This is a package in NPM for HTTP calls. It exists for quite a long time. If you look at the current version, it has 20 dependencies itself, and there is 29,000 other packages within NPM only depending on it. So a huge number of people depend on this package. So I try to look at what is the history of this particular package. There's just one example, there's lots of other packages I could cite. Well, we have lots of things to choose. There is more than 500,000 packages available on NPM, so pick your choice. At some point in time, I don't know the exact date, but version 2.10, this was the dependency graph of this package. So it's a very simple package, we can see it, everyone can depend on it, there is no harm. If you trust this package and you know what it's doing, you can use it. Some version later, this package depends on 2 other packages and transitively on 5 other packages, still quite manageable. Version 2.16, the package directly depends about 15 other packages and some transitive dependencies. Version 2.18, version 2.88. So that's the state today. So this actually shows that even if at some point you started to depend on a package because you thought, okay, it has few dependents, so this transitive dependency problem is not causing any problem for me. Well, since you have to continue upgrading to newer versions, otherwise you have an outdated dependency, well, here you see what happens. And you made a conscious choice of avoiding it, but the evolution makes it so. Another problem that you can see that is very prominent in NPM, and NPM is very specific to this, it's not something that happens in other package managers, package repositories, is the notion of micropackages. It's something that is quite well known in the community. I don't know exactly what is the reason for this, but there is a huge number of NPM packages that are extremely small. So here the example, an example is isArray. Let me take the isArray package. Here you see, this is the full code of the package. Okay, this is basically one single line of code. That's the header of the function, and this is the line of code. That's all it's doing. Okay, that's not, I'm cheating, this is not the only file. There's also a file that's called test.js, which is containing the tests. The test code is 20 times longer than the actual code is testing. So, but actually here you could argue, what's the purpose of depending on this package? I could easily write this code myself. It's open source, I could even just copy paste the code, and then I know it and I can maintain it myself. So that's just one example, but it's really present a lot in NPM packages. In this case, for example, this package, it has, in 2016, it had 27 packages depending on it, but this is direct dependence. If you would look at all indirect dependence, it's again a couple of thousands. And it was very popular, it had 18 million downloads. If you look at the example, I go back here, you would see indeed for the example I produced here, isArray is also part of this one. So it's also here. So there the question is, should you actually depend on very small packages, or is it worthwhile to implement them yourself? Basically here, that's what this guy in his blog, is a well-known NPM developer, wrote. The more dependencies you take on, the more points of failure you have, because you're depending on something that you don't produce yourself, so you don't have you have much less control on it compared to if you would have written the code yourself. Another one, breaking changes. So here, again, I can find many different examples. Breaking changes is related to semantic versioning. Who knows about semantic versioning? Okay. So for those who don't know about semantic versioning, it's quite simple. You have, every version is a 3-digit version number, like here, 1.7.0. 0 means a patch release. You're just making small patches, small bug fixes. The second version number means a minor release. You can make more changes, but you shouldn't make breaking changes in the API, which means that if you depend on the package, you can still safely upgrade to a newer version without it breaking your own dependence. The first release number, if you upgrade this one, then it's breaking changes. Basically, you cannot trust upgrading to a newer version because it will probably affect the way in which you depend on it. So if you want to make important changes in your package, and you know that it will break some of your dependents, you should upgrade to the major version number. This is the semantic versioning policy. It's well known to open source developers. It's also recommended to use in the NPM ecosystem. It's recommended, the problem is it's a policy, so it cannot be enforced. There is no way you can enforce it, except if you would have a tool that can detect automatically if there is breaking changes, but it is it's an undecidable problem in general, so it's not possible to do this. So it's just a policy, which means that there's always people that are not respecting the policy. So this was an example where this developer, the developer of underscore, does not respect the policy, and for example here at some point in a minor release, 1.7.0, so he just upgraded the minor version number rather than the major one. It introduced lots of breaking changes, and all packages depending on them suddenly, because they assumed that whenever they upgrade to a minor release, it still works. Well, it didn't. So they had to go back to an older version because they were assuming that it was okay to upgrade, but it didn't work. This actually caused lots of persons to no longer depend on this package and go to one of its competitors, which is Lodash. I think underscore and Lodash are libraries for doing functional programming and other utilities for JavaScript. Okay, another, of course, obvious problem of software health is security vulnerabilities. I guess most of you have heard about the Equifax problem. This is one of the most recent big ones that I know of. I mentioned this one because it's related to web application vulnerability. So there basically it was a really major problem because it affected, well, 143 million people, the data of 143 million people became exposed because of a known security vulnerability. So basically there was some problem in some application that this website was using where there was a security problem, and a patch was available in March, and attackers actually, they knew about this security problem, and in May they actually started attacking the system to get the data. So the problem was that although in March the vulnerability was known, the developers of Equifax didn't really take advantage of the fact that it was known and try to fix the problem as soon as possible. So 2 months later, the problem was still there and it was not fixed. So you could ask, okay, why didn't they actually fix it? Basically, that's the second part. Okay, there's lots of text here. You can look at the full article if you want. But basically, it's, again, the dependency problem. It was a very hard problem because their software was quite complex and it depended on external apps and older version and outdated versions. So they really had a lot of problems with trying to patch the security hole, and 2 months was simply not enough for them. And because of this, they were stuck with this problem. Another well-known problem is this one, the OpenSSL heartbleed bug. There I'm not going to go in details there, but basically this is an example where of evidence where, okay, it's a vulnerability that was introduced in 2012, and the discovery of the vulnerability was only in April 2014. So this is an example where it shows that sometimes vulnerabilities will linger for a very long time, in this case 2 years, before they are actually discovered. So this means that if some attacker would have known about the vulnerability, he could, during 2 years, have exploited it. Even after its discovery, there's still lots of websites that for a couple of more months or even years continued to depend on the vulnerable version of this package. So these are the types of things that we are interested in analyzing to find out, okay, these are just some examples of some packages that have problems. What we want to know now is how frequent are these problems, how big is the problem if you look at the entire ecosystem. So this can be the entire ecosystem of NPM packages, but in a recent work that is shown here, we have done a similar analysis for 7 different package managers, NPM, CRAN, CPAN, NuGet, RubyGems, Packagists, and I forgot the logo that this one, I don't know anymore which is the other one. So here the focus is on NPM, but in some of the other figures I will show later, you will see three different graphs: one for NPM, one for packages, and one for CRAN, to just show the variation in what we found. So just to show you the size of the data we have been analyzing in, I think it was in July 2017, we extracted data for 426,000 packages. It's a little bit less than the number of packages in NPM because there is some strange packages that you don't want to analyze because they are actually not real packages. 3 million package releases and 13 million package dependencies. Only runtime package dependencies, only those that you will actually install when you deploy your package. So the growth of your ecosystem, so I said there is the increasing complexity. That's one of the famous laws of software evolution. Whenever you continue maintaining your software, it will continue to grow in size, in complexity, and it will be reducing in quality. So here we find clear evidence of this. So there's 3 graphs here that are showing the growth with different metrics, but you should notice that the y-axis are in logarithmic scale. So it looks like a normal growth, but it's actually an exponential growth, because this is a linear growth on a logarithmic scale, which means exponential growth. So basically that's what we found. We found that for all of the ecosystems, they are exponentially growing in size, regardless of whether you measure it in terms of number of packages, number of dependencies, or number of updates to already existing packages. So you see basically the same type of phenomenon depending on, regardless of how you measure things. And what you can also see, the blue curve is the one for NPM. It's clearly at least one order of magnitude bigger than for the other systems. So the green one is Packagist for PHP, and the blue one is NPM for JavaScript. And then you have CRUN for the R programming languages, which is the best of class, which is always, this is basically linear growth. So that's one of the best ones. Basically, it's because they have a very specific way of doing their versioning. They only have one version, one stable version that people have to use, and you cannot really depend on older versions. Which is good, but leads to other problems. So this is about the growth. Then we wanted to look a little bit deeper in this problem of transitive dependencies. How abundant is this notion of transitive dependencies? Because there are so many packages, we only looked at what we call the top-level packages. Packages that are at the boundaries of your dependency graph, so that don't have any incoming dependencies. So no other NPM package is depending on them. For this, we computed the transitive, the depth of the depth of the dependency tree. How many levels deep can you go for finding dependencies of dependencies of dependencies of dependencies, and so on. So there, basically, here you can see this on the right-hand side. If you look at all top-level packages, there is a huge number of packages that have 6 or more transitive levels of dependencies. So this was really surprising to us. It's also something we found only for NPM and much less for the other packaging ecosystems we analyzed. I think it's due again to this notion of micropackages. Well, apparently, so it's really ecosystem specific. It was not found in the other ecosystems. What we also find here you can see the growth. Basically, how does this average dependency depth of packages grow over time? You can see that it remains more or less stable. It's growing a little bit for most of the ecosystems, including CRUN and packages, but it's growing much faster for NPM. The problem is getting worse over time. It's not getting exponentially worse, but it is getting exponentially worse because this is the average, but if you would look at the distribution, compared to this, it will become more and more problematic. It just seems to stabilize here. Maybe this is due because of the left-pad incident where they actually learned about it and said, okay, maybe we are really doing something wrong. I don't know, because we would need the numbers for 2018 to find this out, and we stopped our analysis in 2017. Well, here you can see the same. So there basically we try to quantify somehow to be able to replicate the left-pad incident over an entire ecosystem. So if you would simply say, okay, I take left-pad, and I know left-pad at the time it had a problem, it basically cost more than 5,400 packages to break. So we have these numbers, we know how many problems were caused by this single package. And this was, at that moment, it was 2% of all possible packages in the ecosystem of NPM at that moment in time. So there we now say, okay, let's just compute some metric that says, suppose we don't take 2% of all packages, but 5%. And then we see how many packages in your ecosystem would, if they break, impact at least 5% of all the other packages in your ecosystem. Of course, this is changing in time because the size of your ecosystem is growing over time. But here you can see, again, this is for NPM, the number of packages that will be really fragile and might potentially break 5% of all other packages, directly or indirectly. You see how big it's growing for NPM, while it's stable for the other two, more or less stable. So there is really a huge impact because of the combination of transitive dependencies and stuff like this. So here again we see this peak in March 2016, where we see a decrease, and I hope they actually start to continue to decrease, but I don't think so. Based on the latest results we have achieved, it looks more or less stable. I don't think it's increasing again, but it's still much higher than for the others. Okay, so here for these transitive dependencies, what can we learn about this so far? Clearly it's a problem to have too many transitive dependencies, and just one single transitive dependency, if it's harmful, it can break your entire software. It can break lots of different packages that depend on it. And the problem is, in most cases, you are unaware of it because it can be somewhere very deep down your transitive tree. And so the best way to be aware of it would be to have monitoring tools, dependency monitoring tools or quantity analysis tools that can help you to detect at least the problems. This is mainly for, basically I would say, for software developers that develop these tools, try to make them aware of transitive dependencies as well. But then we have scalability problems, so it's not that easy. Next point was security vulnerabilities. We also wanted to analyze how important is this in the NPM ecosystem. Just as a reference, so this is another paper that by other researchers that are focusing on software security vulnerabilities. It's quite interesting paper to read because it's directly related to the development of websites that include at least some JavaScript library, and basically they wanted to know to which extent are vulnerabilities in the NPM packages affecting websites that are running today. And there what they found is that 37%, so they took some sample of existing websites based on some analysis, I don't know the details, and they found that 37% of all websites include a JavaScript library from which it is known that it has an open source vulnerability. So it's using some version of some vulnerable NPM package. So it's quite an important percentage, more than 1 out of 3. So this is for websites. We had a more general notion. We just wanted to know, okay, not only websites, but how is it the same if you just look at packages in NPM that depend on other packages? Do we find the same kind of percentages? So there basically, there's 3 questions we try to ask. How long does it take if there is a vulnerability that's introduced somewhere? How long does it take to discover the vulnerability? So what is the time needed for discovering a vulnerability that has been introduced? We have seen for the second example, the heartbleed bug, it was 2 years, so sometimes it can be quite long. So here you can see some analysis. Okay, this is survival analysis, it's kind of statistical analysis technique. I'm not going to bother you with the details because it's quite difficult to explain, but I can explain some very, very easily some parts. Basically here you can see that this is the timeline. So here you can see this is 2 years, 24 months. This is 40%. Basically, if you see here, what this means is that after 2 years, there is still, from all of the vulnerabilities that were introduced at some point, after 2 years, still 40% of them are not fixed, regardless of if it's a low or medium or high severity vulnerability. So for more than 40% of all vulnerabilities, it takes more than 2 years to fix them. That's a quite long time. Why does it take so much time? Strange. I will come back to the reasons why this might be the case. So that's the time it takes for discovering a vulnerability. Next thing is, when you discover a vulnerability, you would like to fix the vulnerability. How long does it take to fix a vulnerability once it's discovered? Hopefully it will take less time. If it takes another 2 years, then you're really screwed. 2 years for discovering and then 2 years for fixing it. So here, basically, you can see, okay, the curve is different from the previous one. It's going down much more rapidly, which is good. Basically, if I just take the same interpretation based on one value, after 12 months, which is more or less here, there is still 20% of all vulnerabilities that were discovered, but that have not been fixed. So 1 out of 5 vulnerabilities are not fixed after more than 1 year. It's still quite a lot. It's less than for the other case. So again, what is the reason why quite a big number of packages are not fixed, even if there is a known vulnerability? One of the reasons is because many of these packages are simply unmaintained. They are there, they are lingering, but no one is taking care of them. So there's not even anyone aware that there is a vulnerability problem. Then the third question related to it was related to the dependencies. You have a package, it has been fixed, there is a vulnerability that has been fixed, but now you have another package that depends on this package, and it depends on an older version of your package that still has the vulnerability. How long does it take before your dependency will be upgraded to benefit from the fix? So this is again some analysis we have done. Basically, here is the takeaway message. It takes a long time. It takes much longer to adopt a fixed release than for the packages. So once the release is fixed in the package, the dependents still take quite a long time before adopting it, on average. So basically, here, maybe this one is easier to see. Just look at the blue lines, these are the proportion. Basically, we try to find out, are there actually packages that depend on a vulnerable package and that are never fixed, so that never fix their vulnerability. And here you can see the proportions. The proportions in blue are somewhere around 30 to 40%. Basically, which means that 1 out of 3 packages that depend on a vulnerable package never update to a fix of this vulnerability. That is, so this is this 33% corresponding to the 37% of websites. So that's really annoying. What are the possible reasons for this? One reason I already mentioned before is basically dependent packages. They are actually no longer actively maintained. There is no one taking care of this package, so it's still there in the repository, but it's not being updated because there is no one there to develop it anymore. Once the package is on NPM, it's open source, it will stay there forever. Basically because of the leftpad incident, you can no longer remove packages. Another thing is, basically, so for some packages, the maintainers of these packages, even if it is actively maintained, they are not aware of the vulnerability, or they are not aware that there is a fix of the vulnerability. This could be because these package maintainers are simply not using any dependency management tool or any security management tool that allows them to get informed about security fixes in dependent packages. There are tools like this that exist, but typically you have to pay for them, and if you don't have the money for this, you will not use them. There's also open source tools, but they are much less complete. Third reason, maybe they are aware of the fix, they are aware of the vulnerability, but they cannot upgrade to the new version of the no longer vulnerable dependency because it's incompatible with their current version. So it takes too much effort to upgrade to the new version, and it takes a long time to deal with the problem. And then another one, which is related to the dependency constraints. Basically, it's related to the use of semantic versioning. So sometimes you can simply see, if you, as a developer, you can say, I have a package and I depend on exactly this version of that package. If there is an upgrade, an automatic fix of your dependent, since you say, I have to depend on this particular version of that package, you will not be able to automatically benefit from the security fix. If you would use semantic versioning, you could have a looser dependency constraint which simply says, whatever new patch of my dependent package is available, I will automatically depend on this new version, or whatever minor release of my dependent package is available, I will automatically take this newer version. In that case, you have a less strict dependency constraint, which allows you to benefit from automatic fixes and security fixes and bug fixes in your dependence. Okay, so basically what we see here is that one of the reasons of this problem has to do with the fact that packages are outdated, and by outdated I mean that they still use an older version of some of their dependent packages. They use an older version of some of their dependencies while they could benefit from using a newer version. So this is what we call technical lag. That's our most recent research. It's also known as dependency freshness. So we would like to know how frequently do we encounter packages in NPM that are outdated, so they could actually depend on newer versions of their dependencies. And basically what we found there is, if you look only at the package dependencies, 1 out of 4 is outdated. You could have a dependency to a newer version. And for the package releases themselves, still again, 1 out of 4 is outdated, and it's even worse. The outdatedness is more than 9 months. So there is a newer version of some dependency available for more than 9 months, and it still didn't update. Maybe there's valid reasons for this, but it's still outdated. And the main moment when you update your dependencies is whenever you release a new major update of your own package. This makes sense because then you have time to do this. But what is a bit strange is that whenever there is a minor or a patch update of your dependency, it tends to increase the amount of how to call it, outdatedness, which is strange because if you would adopt the semantic versioning principles, you could automatically upgrade to a newer version of your dependency, while knowing that it should be backward compatible changes. So there basically what we try to see is, can we actually reduce these percentages of outdatedness? And we did some kind of what-if analysis. Suppose that the types of dependency constraints used by your packages are more flexible. They are not strict constraints, but you actually allow to upgrade to automatically to new patch releases or new minor releases. Would this help? Basically, we did this analysis and we found that indeed, if you would do this, if people would be more respecting the semantic versioning principles, 17% of all releases would be more up to date than they are today. Again, for these types of things, knowing if your package is outdated, with as a corollary, knowing that your package is probably less risky with respect to security vulnerabilities, dependency monitoring tools can help you to do this automatically. Most of the tools, many of the tools have some support for this. The problem, of course, is that sometimes it is not easy to upgrade to a new release. So in that case, the developers of the packages that have dependents should provide as much help as possible to help their dependents to upgrade to their new versions. Or another thing is, maybe sometimes your package is still, you depend on some package, but on a previous major version, and just upgrading to a new major version of your dependence is way too costly because it cannot be done, it's not compatible. In that case, doing backports of your bug or security fixes to older major versions might also help to reduce the risk of security vulnerabilities. So that's nearing the end of my talk. Probably also the time is almost up. How many minutes?
7 minutes.
Okay, perfect. So try to summarize all of this and take some takeaway messages that are now supposedly and hopefully independent of the NPM package ecosystem itself. Any type of software where you have dependencies, for these the rules or the guidelines should be applicable. The first one is the following one. Basically, try to not depend too much on other packages. Sometimes you have to because it's really useful to reuse functionality available in libraries, but only do it if it's really needed, if it's helpful, if it's cost effective. But avoid having too many dependencies. For direct dependencies it's easy, so don't have packages that have 100 direct dependencies, that's way too much. Especially because if then you will look at the transitive dependencies, it will start to explode. And also, whenever, before depending on a package, just look at the package you want to depend on. Is it a trustworthy package? Can you trust the package that you want to depend on? Well, you can do lots of analysis. If you know that the package you want to depend on has already today security vulnerabilities, of course, don't depend on it. If it had a high number of security vulnerabilities in the past, maybe you shouldn't depend on it because it's a risky package. If the package is unmaintained or deprecated, unmaintained, very easy, you go to GitHub, you look at the activity log and you see if there is no activity whatsoever in your package, it's unmaintained, so don't depend on it. Deprecated packages, don't depend on it. Packages with low quality code, that's already a little bit more difficult. How are you going to analyze this? You need some code analysis tools. If you can do this, you can also know it. In NPM there is a website called npm.js, which also has some kind of quality analysis, and it gives you a rating for the quality, maintainability, and I forgot the other one. It gives 3 percentages, a score from 0 to 100%, and based on this you can see how good your package is and if it's okay to depend on it. Second thing is, okay, whenever you have your packages that depend on other packages, try to be agile. Whenever you detect a vulnerability, try to fix it as much as possible. This holds both for the package you're developing yourself, but also for the dependents whenever you depend on a vulnerable package. Embrace semantic versioning. Semantic versioning is there to help you, so trust it and use it. But of course, before using it, check that those packages on which you depend also embrace semantic versioning, otherwise you're again in trouble. And use dependency monitoring tools, use quality analysis tools to help you whenever you develop your code. And put all of this in a continuous integration process like this. Whenever you do changes, you will automatically be informed. Even many of these monitoring tools will also do push messages. Whenever there is a problem, they will inform you, even if you don't have a new version available, so that you are aware of the vulnerability. If you're developing packages that have dependents, so that people depend on, then you should try to be as communicative as possible. So whenever you are planning a new update of your package, in that case, you should plan ahead your updates. You should inform your dependents that there is a new major version or minor version even coming up. There will be some features in the new version that will be deprecated. You can use the deprecation use the deprecation features of your favorite programming language for doing this. And you should adhere to semantic versioning. So if you know that your changes will be backward incompatible, do a major upgrade and not a minor upgrade. Whenever your dependents need to upgrade, try to make the life of your dependents, so the packages that depend on you, as easy as possible. So provide guidelines about how they should, maybe it's not migration but upgrading, how they should upgrade to the newer version. Preferably have maybe some automated tool that they can help to do the upgrade automatically. If this is not possible, just provide alpha and beta releases of your package, so that even before launching the real new major or minor upgrade, people can already test if it would work for them by just temporarily installing an alpha or beta release. Or you can even use automated testing. If your dependents have unit tests or other types of tests that are available, you can actually try to run your new version of your package with the unit tests of your dependents to see if it would break the tests of your dependent package. Also there is tools starting to become available for doing this. So it's like, I would say this is a kind of dependency aware or ecosystem aware testing. Okay, so that's basically the lessons learned for today. I hope you learned at least some things about it. If this is not too much related to Drupal, my apologies, but I cannot really talk about Drupal since I'm not a Drupal developer myself. So maybe just one slide before stopping. If this general idea of software health interests you, we are organizing an international workshop to talk about this issue. It's maybe an opportunity to go to Montreal for holidays. Basically, there the goal of it's within this chaos community is to talk about software health issues between academia, industry, and open source communities to see what are the current problems, what are the tools that are currently being proposed, and how can we go further for any type of software health aspect, whether it be social or technical or business or legally related. If this interests you, I have some flyers over there that you can take, or you can just look at this website for more information. That's it. For the remainder, I just want to, as usual, thank all the sponsors for making this event happen. I really like these types of open source initiative communities and gatherings. It's always very useful to meet people there. Thanks. Any questions?
Are your slides available?
My slides are already available on SlideShare. I don't know if I can also send them to someone, to Nick, for example, and he can make this available to the community in another means. Okay. Yeah.
How did Maven score in your analytics?
Maven, we were not. We tried to analyze Maven, but the problem is for the dependency analysis for Maven, it's not. It has a very specific way of doing dependency analysis, and the data source we used was not reliable. So we used a tool called libraries.io, which did the extraction of all the dependency analysis for all the package management ecosystems. When looking at the Maven data, they have Maven data, it was not complete at all. Maybe for 60% of the dependencies they were there, but for the others not. And basically it's related to the way in which Maven deals with dependencies, because dependencies in what's the name of your I forgot the name of the file type in which you specify your in the POM XML files. You have these dependencies, but you can have one POM XML file that uses other POM XML files. You can have templates within them, and basically for finding all possible dependencies from one Maven package to another, you need to do a lot of dynamic analysis to find out what are the actual dependencies. So now that's also something we are trying to do right now, to have this type of data, but it's really much more difficult than for the others, because they have a more dynamic dependency resolution mechanism than the others that are more static, which is, well, it's good for developers, but it's for people analyzing it, it's more difficult. But one of the things I can say about Maven is, for example, related to the semantic versioning. There have been some studies, and basically for Maven, Java developers are not respecting semantic versioning at all. Not at all. So basically, whenever you depend on another package, you restrict yourself to exactly that version of that package. There might be lots of newer versions, you will not depend on it. There might be security fixes, you will not depend on it. And this means that the problem of security vulnerabilities is likely to be much worse in the Java world than in the NPM world, because of the strict dependencies, even though Maven also is supposed to promote semantic versioning. Java developers simply don't use it. I can give you a pointer to that paper if you want. It's 2016, I think.
We are kind of over time, so.
Okay, thanks.